So in this presentation, we're going to look at what happens if we change the pressure that drives the flow through just a converging nozzle. All right, so our scenario is we have some pressure upstream here, some P initial, P naught. We have some pressure right at the exit, P sub E. And then we have some back pressure, which we control. So that's when this says this valve to adjust the back pressure. That's this P sub B. And that's what we're going to actually change. So when we look down on this plot here, what we're applying is pressure on the y-axis. On the x-axis, just position in our nozzle. What is the pressure at different locations within the nozzle? So initially we start out with the back pressure being equal to the exit pressure, which is also equal to the pressure at the inlet. So you see here in case A, it's constant all the way across. If there's no pressure difference, nothing's moving. All right, so here we have a stagnant flow, nothing's happening, nothing's moving. For case B now, we adjust the back pressure to just decrease slightly. And then when we do that, we see the pressure decreases slightly here at the end, and it works its way, excuse me, increases as you go back up the nozzle. Or, better yet, it's higher at the inlet to the nozzle, and then decreases as we come to the inlet. All right. You can think of the back pressure as kind of the atmosphere. If this is a nozzle that we take up in up higher and higher altitudes, that would reduce this back pressure value. If we reduce it some more to case C, the back pressure is down at this point, you can see the pressure drop translates upstream and can be felt all the way back to, pretty far up into the nozzle before you see constant cross section. We can decrease it even further now. We're going to increase the back pressure down to what we have here at case D. Now, at this point, the back pressure equals P star. So you have to look at P star on your handout. But P star is the critical pressure. This is the pressure where if we go any further, or this is the pressure at which we've achieved Mach 1 at the exit. So in case D, we've achieved Mach 1 right there at the exit. And again, that information is transferred upstream into the nozzle. So the pressure drops as it goes through the nozzle before it gets down to point D. So here's the kicker. If we drop the pressure even further to case E, so here the back pressure is reduced to this point, somewhere below the critical pressure. And while that's all well and good, what happens, we have to go from D down to E. The Mach number will never increase beyond Mach 1 at the exit of a converging nozzle. So how do we get from this pressure down to this back pressure? How do we get from this exit pressure up here at P critical down to this back pressure, which is lower than our P star or P critical value? Well, you have to have some type of expansion that happens. So there's this sudden expansion that occurs right at the exit, after the exit from the nozzle, and that's how we can expand down to the that lower pressure. But inside the nozzle, as we go from D to E, the nozzle has no change, no awareness of what's happening. The mass flow rate stays the same, and all the pressures stay the same in the nozzle. So as far as the nozzle is concerned, it doesn't know that the back pressure is reduced from where it was at case D down to case E. And so that's when we looked at the bull jumping into the crowd. That signal up here at A, B, and C, the change shown here at the exit was propagated up into the nozzle, even down to D. But when we went to E, now that information, this lower pressure doesn't propagate up in the nozzle. The nozzle does not change as a result of the pressure dropping even lower. All right, and so we can look at this on some other plots, which I'll show you on the next slide. So here we have, we can see two things. We're going to look at the mass flow rate versus this pressure ratio. So it's the back pressure over the inlet pressure. And then over here, we're going to have the same back pressure over the inlet pressure on the horizontal axis. And on the vertical axis, we'll look at the exit pressure versus the initial pressure in the nozzle. So let's start here on the left. All right, so when the back pressure is equal to the initial pressure, we're at a value of 1. And if that's the case, the back pressure is the same as the inlet pressure, right? There's no flow. So that's why the mass flow rate is 0 for case A. All right. If we reduce the back pressure slightly, now we're going to maintain the initial pressure constant. You could say it increases versus the back pressure, but we're going to look at kind of the similar case that we had in the previous slide where the back pressure is decreasing. So if we decrease the denominator, all right, so what happens is we go up here to B, all right, so our value is getting lower, we're moving to the left, and the mass flow rate increases slightly from A. So A was at 0, so now we're up to B. If we decrease the back pressure a little bit more, you can see a rapid increase up there to C. All right. If we decrease the back pressure even more, we ended up at D. So mass flow rates increased even more. But now, if we decrease the back pressure any more beyond D, it doesn't matter. We're going to be at constant value at all pressures less than whatever that ratio was at point D. All right. So even E out here has the same mass flow rate. So that's, again, the choked condition. Mach number equal to 1 at the exit and not changing anywhere inside the nozzle after we get to point D. All right, so that's, again, I forget if I mentioned on the previous slide, so that's a choked condition. And we'll talk a little bit more about that on Thursday or in our next class. So we have, again, back pressure over the initial pressure here. And so at the case when the back pressure equals the initial pressure, we're here at 1. And over here, the exit pressure also equals the back pressure at 1. All right, we reduce the back pressure just a little bit. All right, we're going to move here. We're going to move to the left on our plot. The back pressure reduces just a little bit. We move down, but also the exit pressure is going to be the same as the back pressure for case B, C, and D. So the exit pressure will be the same as the back pressure until we reach choke conditions, until we reach the critical pressure. Once we reach the critical pressure, right, no matter what we do to decrease the back pressure even more, the exit pressure will not change. So just like with the mass flow rate over here, it's constant from D to any lower pressures for the back pressure. Same case here, we have it case D. If we drop the back pressure even more, the exit pressure stays constant at the critical pressure P star.